Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll be discussing incidence geometries. More specifically, I'll be talking about what's called incidence geometry. I'll define it and discuss some models of incidence geometry. And then I'll discuss a theorem about intersecting lines in incidence geometry. This video is produced for Ohio University Math 3110-5110 College Geometry. The content corresponds to material in section 2.1 of the book Geometry, a Metric Approach with Models by Millman and Parker, and more specifically, just pages 22 to 24. The corresponding homework is this collection of 5 exercises from section 2.1. Now recall from the previous video the definition of abstract geometry. An abstract geometry is an ordered pair consisting of a symbol on the left that denotes a set called the set of points, and a symbol on the right which denotes a set called the set of lines, and lines are sets of points. And those sets of points, those lines and those points, have to satisfy these two requirements that are called axioms. For every two distinct points, A and B, in the set of points, there exists at least one line L in the set of lines, such that points A and B are elements of that line. That's one requirement, one axiom. The other axiom is this: for every line in the set of lines, there exists at least two distinct points that are elements of the line. Those two requirements are called the abstract geometry axioms. They're simply the requirements that P and L must satisfy, in addition to L being non-empty, in order for this ordered pair to be qualified to be called an abstract geometry. Now I want to introduce what's called incidence geometry. An incidence geometry is an abstract geometry, one of those things, a P, L, that satisfies the following two additional requirements, are called axioms. For any two distinct points, A and B, in the set of points, there exists exactly one line, L, in the set of lines that both points lie on. Remember, in the definition of abstract geometry, there had to exist at least one line that both points lie on. So in incidence geometry, the requirement is more stringent. There has to exist exactly one line. That's incidence geometry axiom number 1. Axiom 2 is this: there exist at least 3 non-collinear points. Those requirements are called the incidence geometry axioms. Now keep in mind that in order for an ordered pair, script P, script L, to be qualified to be called an incidence geometry, that pair must satisfy not just these incidence geometry axioms, but also the abstract geometry axioms. Because remember, an incidence geometry is an abstract geometry that satisfies these extra requirements. So that means an incidence geometry has to satisfy these two axioms and these two axioms. Let's discuss models of incidence geometries. Remember, a model is just simply an example. So I'm going to start by discussing finite geometries. We're going to revisit pairs, script P, script L, from the previous video, and we're going to discuss whether or not those pairs are qualified to be called incidence geometries. So we'll start with this pair. And remember, there's a typo in this pair. There should not be an AE here. So the question is this pair qualified to be called an incidence geometry? Explain why or why not. Well, the quick answer is no, because it is not qualified to even be called an abstract geometry. So since that pair, script P, script L, is not qualified to be called an abstract geometry, it also cannot be an incidence geometry. Because remember, an incidence geometry is a special kind of abstract geometry. Question B, consider this pair. illustrated this way. Is this qualified to be an incidence geometry? Well, remember from the previous video, this is an abstract geometry. Let's remember the abstract geometry axioms. For any two distinct points, there exists at least one line that they both lie on. And for every line, there exists at least 2 points that lie on that line. So any 2 points in that set lie on at least one line. And any line in the set of lines contains at least 2 points. So this is an abstract geometry. Is it qualified to be called an incidence geometry? So the requirement for that is, in addition, we have to satisfy these incidence axioms. For any 2 distinct points, there exists exactly one line that they both lie on. And there must exist at least 3 non-collinear points. Well, clearly this satisfies axiom 1. For any pair of points, there is exactly one line they both lie on. Now we need to see about Incidence Axiom 2. Do there exist 3 non-collinear points? Well, notice A, B, and C are 3 points, and there is no line that all 3 points lie on. All right, let's go on. Question C. This example from the previous video. That set of points, A, B, C, D, and this set of lines. Remember that that line B, C, D is that dotted thing in the diagram. Is this qualified to be an incidence geometry? Well, let's remember that this is an abstract geometry. And let's actually be more explicit. Let's just point out that it satisfies abstract axiom 1. Good. Every 2 points has at least one line that they both lie on. And it satisfies axiom 2. Abstract axiom 2, I should say. Notice that every line contains at least 2 points. One line contains 3 points. That's okay. Now what about the incidence axioms? Well, it also satisfies the incidence axioms. Let's check. Axiom 1 says that for any 2 points, there's exactly one line that they both lie on. Remember that B and D lie on that line, that dotted thing. C and D lie on one line, that dotted thing. And C and B lie on one line, that dotted thing. What about incidence axiom 2? Do there exist 3 non-collinear points? Well, look, there are 3 points that are collinear. They're not non-collinear. But that's okay, because axiom 2 doesn't say that all sets of 3 points have to be non-collinear. Axiom 2 just says there must exist at least 3 non-collinear points. It doesn't mean that all sets of 3 points have to be non-collinear. So look, points A, B, C are non-collinear. There is no line that contains all 3. So this is an incidence geometry. And we knew from before that this was also an abstract geometry. So let's go back and add those notes to our previous examples. Example A, this was not an abstract geometry. Let's go on. What about this example? Remember from the previous video that this example was an abstract geometry. Let's remind ourselves why. Abstract axiom 1 says that for any pair of points, there is at least one line that both points lie on. Now look, the pair BD, for instance, lie together on this line. They also lie together on this line. That's okay. There has to be at least one line they both lie on. So we passed abstract axiom 1. What about abstract axiom 2? That says that each line has to contain at least 2 points. Well, every line does contain at least 2 points. One line contains 3 points. That's okay. Now what about incidence axiom 1? Does every pair of points have exactly one line they both lie on? Well, for a lot of pairs of points, there is exactly one line. For A and B, there's exactly one line they both lie on. For A and C, there's exactly one line they both lie on. For A and D, there's exactly one line that they both lie on. For B and C, there's exactly one line that B and C lie on. B and C only lie on that one dotted line. But for the pair B and D, there are 2 lines that both B and D lie on, so it fails. Because B and D both lie on 2 lines. So this is not an incidence geometry. Now just for kicks, let's consider if this abstract geometry would have passed Incidence Axiom 2. Do there exist 3 non-collinear points? Well, yes, A, B, C are non-collinear. So it passes Axiom 2, but it fails Axiom 1, Incidence Axiom 1, so it's not an incidence geometry. Let's consider this pair. From the previous video, we saw that this was an abstract geometry. Let's remember the axioms that it satisfies. Abstract axiom 1 says that every pair of points has exactly one line they both lie on. Now remember, there's a typo here. We discussed how points A and B lie together on this line. Points B and C lie together on that line. Points A and C lie together on that same line. So every pair of points has a line that they both lie on. What about abstract axiom 2? Well, it passed that as well. That was this, that every line has to contain at least 2 points. And we see we've only got one line and it has 3 points on it. Great. So that's why that qualified to be called an abstract geometry. Now let's see about incidence geometry and the axioms that are required to be qualified to be called an incidence geometry. How about incidence axiom 1? Every pair of points has exactly one line that they both lie on. That pair, every pair of points has exactly one line they both lie on. So we've passed incidence axiom 1. What about incidence axiom 2? That axiom says there have to exist 3 points that are not collinear. Ooh, we flunk that. We only have 3 points and they are collinear. So there do not exist 3 non-collinear points. So that means this example is not an incidence geometry. Let's go on. The Cartesian plane is an example, a model of incidence geometry. Now in the previous video we saw that the Cartesian plane is qualified to be called an abstract geometry, and that fact is proven in the book. And that's proposition 2.1.1. In proposition 2.1.4 of the book, it's proven that the Cartesian plane is also qualified to be called an incidence geometry. The bulk of the book's proof is taken up in proving that axiom 1 is satisfied, incidence axiom 1. For every 2 points, there exists exactly one line they both lie on. That portion of the proof is clear enough, and there's no need for me to discuss it here. But the authors leave it to the reader to prove that incidence geometry axiom 2 is satisfied. Now that axiom, remember, is this, that there has to exist a set of 3 non-collinear points. Well, to prove that this axiom is satisfied, you just simply have to produce an example of a set of three non-collinear points. But keep in mind that in presenting an example, you have to not just present the points, but also explain clearly why they're non-collinear. And an example is most useful if it's very simple and involves no computations. So I think it's worth presenting a simple example here so you can see what I mean by that, how simple should be. So consider these points. A is the point 2, 5, B is the point 2, 4, and C is the point 10, 4. Well, you can see that points A and B lie on exactly one line that's a vertical line, and points B and C lie on exactly one line that's a non-vertical line. So there's no way that a single line can contain all three. The only line that contains A and B is going to have to be this one. So A, B, and C are non-collinear in the Cartesian plane. Let's go on. The Poincare plane is also an example, that is a model of an instance geometry. Now, in the previous video, we discussed the fact that the Poincare plane is qualified to be called an abstract geometry, and the fact that the book proves that in Proposition 2.1.2. In book Proposition 2.1.5, it's proven that the Poincare plane is also qualified to be called an incidence geometry. And as with the book's proof of Proposition 2.1.4, the bulk of their proof of Proposition 2.1.5 is taken up in proving that Axiom 1 is satisfied. But as with the book's proof of Proposition 2.1.4, that is the proof that the Cartesian plane is a model of incidence geometry, just as they did in that proof, in the proof of this new proposition, the proposition that the Poincare plane is a model of incidence geometry, in that proof, they leave it to the reader to prove that incidence geometry axiom 2 is satisfied. So again, they don't show that there exist at least three non-collinear points in the Poincare plane. Now, because computations involving Poincare lines can be so messy, it's particularly useful to have a simple example involving no computations. Here's such an example. Consider those same 3 points from before. So this is actually not drawn to scale. I've either written down these coordinates wrong or I plotted this wrong, but that's okay. The main thing is you can see that points A and B have the same x coordinate. So the line that passes through A and B in the Poincare plane is going to be a type 1 line, this thing that looks vertical. Whereas notice that points B and C don't have the same x coordinate. So the line that passes through B and C will be this type 2 line. So the only line that contains A and B is that type 1 line. And the only line that contains B and C is that type 2 line. So therefore, the Poincare line that passes through A and B cannot be the same as the Poincare line that passes through B and C. So that means that A, B, and C are non-collinear in the Poincare plane. But notice that the lines that go through A and B and C look a lot different from the lines that go through A and B and C in the Cartesian plane. Our last example that we'll consider is the Riemann sphere. Now remember, the Riemann sphere is an abstract geometry. It satisfies abstract axiom 1. Given any 2 points on S2, there exists at least one line that passes through both points. Now for some points, there is more than one line, but that's okay in terms of being an abstract geometry. It also satisfies abstract axiom 2. Abstract axiom 2 is that every line contains at least 2 points. But it's not an incidence geometry. So it fails Incidence Axiom 1. If you consider the North and South Pole, for instance, that's a pair of points that has an infinite collection of lines that they both lie on. What about Incidence Axiom 2? Well, it actually passes that. Remember, Incidence Axiom 2 says there must exist 3 points that are non-collinear. Well, there are. Remember, for instance, we can call this point over here point A, and we can call this point B, and A, B, and N are non-collinear. The only great circle that points A and B lie on is the equator. The only great circle that A and N lie on is one of those lines of longitude. Finally, I want to talk about a theorem about intersecting lines in incidence geometry. This theorem says, given two lines L1 and L2 in an incidence geometry, if the intersection of those two lines has two or more distinct points, then those lines are actually the same line. That is, L1 equals L2. Now there's a contrapositive of this theorem, which can be stated as a corollary. So given two lines in an incidence geometry that has symbols denoting lines, if those lines are known to be distinct, that is, if they're known to not be equal as sets, then either those lines don't intersect at all, or they intersect in exactly one point. Now, observe that Theorem 2.1.5 and its corollary are not theorems of abstract geometry. They are theorems of incidence geometry, given lines in an incidence geometry. So those are not theorems of abstract geometry. So indeed, there's a typo here. We've seen examples of an abstract geometry in which two distinct lines intersect in more than one point. Remember this example. In this geometry, we had this green line containing points A, B, and C, and we had this red line containing points B and D. Those were not the same line, but they intersect in 2 points. So those two lines, line BCD, the green thing, and line BD, the red thing, are distinct lines. They're not equal as sets. And they intersect in more than one point. And think about the unit sphere, the Riemann sphere, the equator, and that great circle, that is the line of longitude, intersect in 2 points. Point there and a point there. So those are not the same line. They're distinct lines. They intersect in more than one point. But of course, neither of these examples is an incidence geometry. That's the whole point. These are examples of abstract geometries. So the theorem articulated here is a theorem of incidence geometry. It's a theorem about intersecting lines in incidence geometry. Well, that's the end of the video. Thank you.